Good.
Now it should be working, right?
It's working now, Gregor. Thank you.
Okay. Very well. Yes. Hello again from my side. Let me introduce myself again, as we did this morning. My name is Gregor Weiß. I'm working at HLRS with Flavio and Andreas Rupp, Flavio Galeazzo and Andreas Rupp. And as you see, we have been involved in this task with our partners, Sergey and Henrik from the Wiki GmbH. They have already shown you some very interesting results regarding the parallel I/O, and also Charlie mentioned some enablements that could come from this new developments. So let me start by showing you the objectives of the task, what we were supposed to do, what we planned to do at the beginning of the project, and what could have been already anticipated there. So one thing was to reduce the number of files. This is a problem in OpenFOAM in the legacy format, that you have these processor folders, and then in HPC file systems, you hit very quickly a limit of handling the number of files. And as we minimize the number of files, this would become really an enabling technology, so breaking some of the walls that hindered running OpenFOAM at larger scales. The other part is that actually we, as the title said, the coherent mesh representation, so we thought of a new data representation for OpenFOAM unstructured mesh data, and that optimizes the I/O access pattern. And here lie these time to solution gains that also Sergey was already presenting, that he had 1 order of magnitude for his benchmark case. And essentially, this is also a technology enabler, because if you hit also another limit in HPC clusters, the wall time limits of your queues, then pre-processing with the older format, I will also show that, is really a hard wall that you will hit, and not anymore with this new coherent mesh representation and its parallel I/O capabilities. Exactly. So our approach was to introduce a new contiguous access pattern. I will come to what I mean by the contiguous part, and the opposite of that, and then also using that for the implementing a parallel I/O transport layer in the core OpenFOAM library. To quote our partners also, so this becomes a little bit more emotional, let's say, because they use OpenFOAM on a daily basis, consulting their customers, and then they really want to, so they have this dream, and I guess many users share dreams like that, that you could just run OpenFOAM on any number of cores without decomposed power. So that is one part, or maybe not reconstructing after your parallel run. That's typically something you would have to do. Or if you have all these processor folders and want to change something, some boundary condition, you don't want to step to all the ASCII informations of your boundary fields in all processor folders. And the other part is getting angry emails because of the inode limits. That's regarding the number of files, and so on. So the agenda for today, what I will tell you about today, the story I try to outline is, first of all, I get everybody on the same page with regard parallel I/O on file systems that are HPC relevant, and what does an I/O scheme access pattern mean, and what's the data access pattern of OpenFOAM. Then I will show you this new coherent mesh representation in a second part, and the third part is the actual implementation into OpenFOAM and how it is then again in the time to solution or really enabling technology. So in general, parallel file systems in HPC infrastructures they have one benefit, that they can you can facilitate many connections to many object storage targets, and this way you could actually scale up to terabytes per second. But to do so, you have to stick to some good behavior, let's say, that optimizes the requests and operations, I/O operations to this file system. And one thing is the inodes, as I mentioned before. This is sort of the metadata inside your file system that lets the file system know where the data is stored and which actual hardware on which object storage targets. So they are on this very right side of this graphic here, and in between you have these lookup servers which take care of this inodes of the metadata, and in between your compute nodes and your object targets, you will always have the requests of reading and writing, and these requests should be minimized. And all of these measures here to optimize the number of files, keeping fewer files, but having aggregating them with larger access sizes, and thus also minimizing the number of I/O operations. So these are all good means to optimize or minimize the number of requests to the file system. One parallel I/O library that very much facilitates that is ADIOS2, and that is what also we used in our task here. It has this N by M model, which is meaning the N processor ranks of your parallel simulation. They will write to a M, being smaller than N, number of files. So this way you can actually keep the number of files flexible in ADIOS2. At runtime, you can decide how many files you want to write, and then your aggregating rank will get the data from other ranks for the I/O. Okay, so there are many features in ADIOS2 also that, for instance, the asynchronous writing that very much facilitate a very good parallel I/O schemes. One aspect is ADIOS2 uses exactly this contiguous access pattern. What is this? So contiguous access pattern means that it's the simplest way of thinking how your data is dealt with, that really some array coming from rank 0 is really going into the first chunk of your file, and rank 1 will write into the next chunk. And so everything is determined by a start and size of these chunks or slices of your data, and in opposition to an irregular access pattern, which can of course do some mapping, which might be beneficial if you cannot avoid it. But it will definitely give you some overheads due to reorganization. So what does OpenFOAM look like? The data stored, how is OpenFOAM data stored? It's basically, it's always stuck to the mesh data structure, of course. And here one key part is this face-to-cell connectivity. We have an upward adjacency going from 2D elements, the faces, to the 3D elements, the cells. And here the cell connectivity is stored by these owner and neighbor lists. They are lists that store the owner cell ID indexed by face indices, right, in these owner and neighbor lists. And once you decompose that, everything has to be renumbered. So this is what it would look like if you look into your processor folders inside the polymesh folder in there. Then you will have new files, new face files, new point files, etc., that store all entities with new indices starting from 0. And you will also store these addressing files, the mapping essentially from the old global mesh to your partitioned mesh. And in the end, your mesh gets very much fragmented with respect to the previous global mesh. So it's renumbered and fragmented, which really calls or asks for this irregular IO access pattern. But as I said, if you can avoid it, you can avoid some of the overheads of mapping during the IO. So here comes in the coherent mesh representation that we thought of. It is really simple in terms of that we impose some 2 to 3, let's say, the third rule, 3 ad hoc rules about how to store, how to order the mesh indices. And the third rule is actually also a consequence from the first rule. That's why I'm saying it's 2 to 3 rules. So the first one imposes the upper triangular order, which you are very much familiar. This is what OpenFOAM does already. And also a walking order for faces. What does that mean? So as I walk through the cells, as I incrementally walk through cells, I enumerate and the faces, and those faces are owned by that cell. So the first cell here owns all the first 4 faces. And then I step into the next cell and I enumerate the new faces that are not numbered yet. And those are also owned by cell 1, and so on. Okay. And the same is done for the points. The points after you have enumerated your faces, the points will be numbered by the incremental occurrence in the face lists. So far, so good. Then the third rule is, as I said, it's a mere consequence from the first rule, because once you have it ordered in this way, your owner list, which was this face to cell connectivity, can be flipped, because your owner list will look like chunks of equal cell indices. So you will read something like 0, 0, 0, 1, 1, 1, 2, 2, 2, etc. So you can basically flip it around by storing this owner start list. So it's always the first phase of a cell. It's a list indexed by cell ID, and it's the first face ID that is owned by that cell. It's as simple as that. Okay. Now, what does all of this give me? If I now want to split the mesh, if I want to partition it or really read a chunk, really, I'm not talking about a good partitioning of what a decomposer would yield, but really just chunking for reading to get this contiguous IO access pattern. It's really easy to simply read the first chunk from your owner list, or the owner start list, sorry, and determine exactly the chunk of lists that are face ordered. So the faces as well as the neighbor list will be face ordered lists. And then from the faces, I see the maximum point ID, which I have to read for that slice to get the points. So I have a coherence going from my 3D elements to 2D to the 0D points. And going away from this particular example, this is generally speaking, it's a tree-based data structure now, which is parallel. So it's or very easily partitioned or sliceable. So we have a coherence to our dimensionality layers and a sliceability across processors. Okay, so what we did to implement this into OpenFOAM, and especially regarding IO, let's have a look what IO looks like in the OpenFOAM API. So definitely that's something as a user you're used to, that there are these insertion and extraction operators, and that's something which we want to keep. So these are they were designed very serial in the fashion that if you call one of them, they really call the IO to your particular file. So it right away streams whatever you put into your insertion or extraction operators. But now concerting the need of buffering, etc., during parallel I/O is really relevant if you use something like this ADIOS2 library. So we embedded ADIOS2 inside the I/O stream family of classes, inside the bottom I/O core library of OpenFOAM, to enable these streaming operators. But now we have to concert more things of when some particular information comes about your boundary condition, that you buffer that in between. I call this the CFD metadata. And then this is actually stored into one single file. So we have these ASCII files that still give us the CFD metadata, and the hardcore data is also in some sense, or in some cases, it also needs some reorganization. For instance, for surface fields, we will have to integrate the processor boundary patch values into the internal field of the coherent representation, right? Yes. So let's have a look at what the result is. So going away from the API, if you're not interested in that too much, this is what your case will look like. So there are no processor folders anymore. Instead, you will have these ASCII CFD metadata files where you store what kind of boundaries, etc., what your field is, how the size of your field, etc. And this data.bp are these ADIOS2 files that store the hardcore values of the field. The same for the mesh, we have a data.bp, and also for reference, later reference. So what will be implemented definitely is this time coherent format where the ADIOS2 data is stored within a time folder. But in principle, what we also tested and implemented was a case coherent where individual time steps, they all are aggregated into this file that also enables a little bit more, for instance, the asynchronicity feature, HBC relevant workflows, let's say. Yes, and in essence, your parallel and serial case, they always look the same. So there's no difference. Again, there are no processor folders. Yes, that's what is exactly demonstrated here. So the legacy format, what could also be called uncollated format, you have your individual processor folders. It quickly extends to what I can show on this slide. So inodes is really a big bottleneck. Also in the collated format, of course I can collate from 512 processors, I can collate all the output into one processor folder, but it's also not recommended in terms of decent I/O where that gets some performance. You would want to aggregate your data per client, per compute node or something like that. And then quickly it sums up to many more files than really you want to handle. But the new coherent representation always looks the same. It's irrespective of the number of processors, and especially looks just like a serial case. Okay, so this is one of the most interesting slides. This also emphasizes of what could be theoretically demonstrated, but nobody actually wants to demonstrate. So what we demonstrated, what Sergey, for instance, demonstrated, he had this 1 order of magnitude in his pre-processing decomposition. What I did for the cavity case, a 3D cavity case, I saw something similar, that if I decompose here, or I pre-process the case for different mesh sizes, so 1 million to for up to 512 million cells. Do a block mesh and then the decomposition, and that adds up to quickly, if I use the collated format, it quickly adds up to levels where I cannot pre-process it on a 24-hour queue. So this is already the technology enabler. So with the coherent format, I can do this, and I can do it within 45 minutes or something like that. Only the decomposition block mesh also takes some time. So here we already have the one order of magnitude and technology enabler. But why is this so? This is the algorithmic time complexity improvement. So decomposed PAR has nested loops, and those are n squared in time complexity. You see here the data again plotted as these points, and this is the n squared scaling law. And for the coherent format, what we do to employ this first rule is a sorting algorithm, a merge sort essentially, which is n log n in its time complexity. So the actual speed up, or your time to solution factor, it grows with this gap between the n squared and n log n laws, right? So if I compare this now by dividing n squared by n log n, then I see that with 100 million grid cells, I hit this barrier where I would achieve something like an order of magnitude. But as I progress to case sizes of 1 billion cells, and those are the case sizes which are really exascale relevant, then I start getting 2 or 3 orders of magnitude. Again, that's sort of extrapolated here, theoretically reasoned, let's say. Nobody actually wants to demonstrate that. But you see my point, I think. It's really at this point we're at the level of the enabling technology. So that's exactly this point. It's a enabling technology for cases which are exascale relevant, right? For these cases which have 1 billion cells and more. And on all scale, it's true. And the dream has become true, essentially, to start any parallel run from just reading, and also you will not, and that's actually not shown on the right hand side, you will not need the reconstruction. For collated, you will have to have a post-processing step that reconstructs your case. In the coherent format, it's a zero effort. So that's gone totally. And again, I'm repeating myself, your case is, you can handle it as if it is serial. Also, the time of you as an engineer editing something in the ASCII CFD metadata is also gone, or minimized to a minimum. Okay, let me check the timing. Yes, I still have a couple of minutes. Yeah, this is
Actually, you're running out of time, Gregor. So, or 5 minutes.
We started 11:05.
Yeah. Okay. Then
Okay.
go
Sorry.
on. Yes.
Okay. Yes. Okay. I can speed it up. This is, so we did a bunch of tests, as you can see, with the several case sizes. The largest case size which I tested was this 512 million cell case, and we tuned it up. So this was also a question earlier during the workshop. What's the largest case size and what's the largest core count? This was mentioned more than 500 million CPU cores on our Hawk machine at HLRS. Yes, with that, let me conclude. So we achieved what we were supposed to achieve. We reduced the inodes. This is the enabling technology part. And pre and post-processing, whatever you do as an engineer working on the case, there's really a big time to solution gain for you as a user. The case always works as if you work in serial. And also, let me emphasize this coherent mesh representation. It's not limited to OpenFOAM. It's a general representation for a mesh, or for unstructured polyhedral meshes. Future implications. One very interesting part is actually this one, the parallel on-the-fly decomposition. So as I was saying, it it's all about the reading right now. Turning on some parameters after you read it, that would be really HPC mode, that you simply read a mesh and decompose it on the fly in the during the startup phase of your simulation. Also dynamic load balancing, region of interest, doing your post-processing, asynchronous I/O, and many more features are in the realm of implications for that. With that, okay, thank you very much.